Attention everyone, keep your eyes peeled. We are delving into a case that merges cutting-edge observations, discrepancies in data, and remarks from a scientist unafraid to question established beliefs. Atlas has come into our field of analysis with images and measurements that shift several scientific certainties into a realm of uncertainty. In this discussion, I will present in straightforward terms and with precise figures the observations pointed out by Avi Lobo. I will clarify why these observations pose challenges for a natural-only explanation. We will examine the calculations that caused the surprise, introduce the technological hypothesis as a testable proposition, and conclude with 3 objective summaries. These will cover when it was discovered, how its approach has evolved up to November 24, 2025, and what distinguishes it from other interstellar entities. Stay alert as we navigate between technical diagnostics and layman's terms, ensuring you grasp why scientists are calling for measurements that can either confirm or dismiss each line of reasoning. When asked about the images and initial interpretations, Avi Lobo was unequivocal. Authority should not dictate the verdict. It should stem from data. According to Lobo, the clearest images available reveal unexpected emissions around Atlas that align with its motion rather than radially relative to the star that governs our system. This behavior deviates from the typical solar sublimation seen in comets. Lobo highlighted that this plume orientation could indicate various scenarios: reflected light from elongated structures, particle jets exhibiting their own dynamics, or emissions resulting from processes beyond simple thermal sublimation. He stresses that measuring jets' speed and determining their composition are crucial for distinguishing between natural explanations and alternative hypotheses. In essence, Lobo is not closing off any possibilities. He insists the scientific community should treat these observations as a series of testable propositions rather than a narrative already established. This demand for data transforms the conversation from opinion to investigation. In comet physics, we understand that heating from the star that dominates our system causes surface ice to sublimate, allowing gas to escape and push outward radially, creating tails that predominantly point away from the star. When emissions align with motion, it presents a diagnostic signal that requires further scrutiny. Several potential explanations exist for this phenomenon: projection or optical effects in the image, authentic mass emissions directed by local geological features, or ejections driven by a localized source of directional thrust. Each of these choices carries different implications for mass, energy, and origin. Lobo emphasizes that only velocity and composition assessments can differentiate these hypotheses. Measuring the Doppler shift in plume spectral lines, quantifying mass flux, and comparing it with sublimation models is the appropriate course of action. Lobo describes this as a scientific priority. Without these figures, any narrative that seeks to conclude the matter will be hasty. The 3 anomalies that most concern Lobo are as follows. Anomaly 1. Mass and frequency. Lobo points out that objects potentially this massive entering our interplanetary system at the observed frequency would be statistically uncommon. If Atlas is genuinely large, its existence challenges assumptions regarding the density and distribution of interstellar objects. Anomaly 2 relates to its trajectory in the ecliptic plane. The object's path is hyperbolic, retrograde, and nearly parallel to the ecliptic plane. Additionally, this route leads to close gravitational interactions with planets, including an anticipated influence in the vicinity of Jupiter in 2026. For Lobo, these orbital coincidences are statistically striking and warrant explanation. Anomaly 3 concerns the volume of material and the integrity of the nucleus. Images and jet estimates imply significant flows that, if solely attributable to sublimation, would necessitate active areas and energy sources, far exceeding those expected for a nucleus within the size limits inferred from Hubble observations. As Lobo underscores, either the observational figures are misinterpreted or an additional energy source is needed to account for so much ejected material without fragmenting the body. The calculations reveal issues relating to mass, flux, and energy at scale. Lobo and colleagues clearly outline a logical trajectory to highlight the contradiction. Measure the brightness and extent of the plumes. Estimate the density needed to produce that brightness, and pair it with a typical outflow speed to determine mass flux per unit time, revealing figures of enormous magnitude. Utilizing the formula density times speed times area for flux estimations yields values in the billions of tons per month, depending on the parameters selected. Then, when evaluating the energy necessary to sublimate that volume of ice, such as carbon dioxide, whose energy requirements are well documented, the results far exceed what the star that governs our system provides to an area consistent with the estimated nucleus. Lobo's direct conclusion is this: if we stick to a sublimation explanation, we must entertain the idea that the active areas would be absurdly larger than the object itself or propose additional energy sources. Neither scenario is comfortable. This is why Lobo calls for observational tests of alternative scenarios. The technological hypothesis outlines what it entails and what it predicts, Lobo presents responsibly a hypothesis that directionally oriented jets may serve as controlled thrusters, with exhaust aimed toward the star that governs our system to create thrust that alters the trajectory in a regulated manner. From a technical standpoint, this could clarify non-gravitational accelerations in jets that align along the motion vector. It is important to note that this does not assert it is a probe. Rather, it serves as a working hypothesis with concrete observational implications. Artificial thrusters would produce exhaust patterns with compositions differing from icy plumes. Escape velocities and emission spectra would exhibit metallic or molecular signatures that are not common with sublimation. Furthermore, the timing of the jets could reveal controlled on-off directional changes, rather than random thermal fluctuations. The scientific merit of this hypothesis lies precisely in its testability. Lobo maintains that transforming the idea into measurable predictions is what distinguishes it from unfounded speculation. This is where the observational priorities come into play. Lobo explicitly lists the measurements that the community should prioritize. Jet velocity measurement, assessing Doppler shifts in kinematics to compare with thermal sublimation constants, much higher than anticipated velocities would suggest a distinctive source. Composition spectroscopy should target volatile molecules, such as water and carbon dioxide, in addition to traces of metals or unusual molecules that might imply machinery exhaust. Temporal evolution requires continuous observations to determine whether jets respond to control, altering intensity or direction in a systematic pattern, or follow random thermal variability. Absent these three data lines, any conclusions drawn will be provisional. Lobo calls for the synchronization of large telescopes, high-resolution spectrographs, and space observatories to cover all relevant scientific bandwidths. When simple calculations indicate that solar energy striking an area compatible with the nucleus is insufficient to sublimate the ejected material, only a few scenarios remain: observational misinterpretation, unknown cometary physics, or additional energy sources. Lobo presents these options and requests measurements to either confirm or invalidate each one. An observational error would imply that brightness has been misconstrued as mass, when it could correspond to optically efficient particles or scattering processes instead. Unknown physics could involve exotic compounds or exothermic reactions not accounted for in standard models. Additional sources would suggest exactly what many hesitate to voice: an internal mechanism, whether artificial or natural, that transcends mere thermal sublimation. Lobo's approach is scientific: to enumerate hypotheses and convert each into observable predictions. That is the standard he insists upon before we can confidently ascertain what is occurring. When was 3I Atlas discovered? Atlas was publicly recognized on July 1, 2025, by the Atlas system in Chile. The detection was communicated to the Minor Planet Center, initiating an international observation campaign, as hyperbolic trajectory objects are rare and scientifically significant. Pre-discovery observations were subsequently uncovered in archives. As teams typically revisit older images following alerts, initial characterization confirmed the hyperbolic orbit, affirming its interstellar origin. Its velocity and eccentricity indicate it is not gravitationally tied to our star. Following the convention for the third confirmed interstellar visitor, it is designated 3I since its discovery. Networks of ground-based and space-based telescopes have continuously monitored its trajectory, brightness, and activity. Rapid coordination enabled researchers to gather vital data regarding its apparent composition, jets, and orbital parameters, information stimulating scientific debate through November 24, 2025. Documented approach and anomalies that stunned the scientific community. The trajectory of Atlas into our planetary system unfolded in noted stages. It passed relatively near Mars in early October 2025, reached perihelion, the closest point to the star governing our system, in late October 2025, and was on course for a window of enhanced visibility from Earth, expected mid-December 2025. Observatories and spacecraft, including the Mars Reconnaissance Orbiter, captured pivotal images and data en route. Higher-resolution images, such as those obtained by the HiRIC camera on October 2, 2025, when the object passed near Mars, along with multiband observations from space telescopes and major ground-based telescopes, provided crucial constraints on nucleus-sized comet activity in the presence of jets. Atlas had already exhibited detectable activity across several bands and indications of non-gravitational acceleration. Warranting deeper investigation, the scientific community consolidated orbital parameters and prioritized forthcoming observation windows, asserting that despite the anomalies, the object posed no risk of impact. Instead, it represented a unique opportunity to examine the properties of a body originating from beyond our system. First, scale and mass. Estimates derived from Hubble images suggest upper limits for 3I Atlas's nucleus that may be considerably larger than anticipated for typical interstellar visitors, with conservative upper limits reaching about 5.6 kilometers in diameter, while allowing for uncertainties to suggest smaller values. This potential for increased mass prompts questions about the origin and frequency of such objects. Second, activity and composition. activity observed at relatively distant positions from the Sun, along with jet patterns and atypical spectral features, sets 3I Atlas apart from previous visitors, while 2I Borisov exhibited behavior more consistent with traditional interstellar comets, and 1I Oumuamua demonstrated asteroid-like characteristics. 3I Atlas combines size, vigorous activity, and features that further complicate interpretation. Third, trajectory and contextual coincidences. Its hyperbolic path and closeness to the ecliptic plane, combined with scheduled planetary encounters, make its arrival statistically noteworthy. The confluence of these factors, scale, activity, and orbital context, justifies the intensive observation campaigns and the keen interest of the scientific community. Avi's statements reflect what science must do in response to anomalies. They propose hypotheses and, crucially, turn those hypotheses into testable predictions. The operational challenge now is to obtain measurements of velocity, composition, and temporal dynamics to validate or challenge each explanation. What are your thoughts regarding the questions posed by Lobo and the discrepancies in the numbers? Could the answer reside in misinterpreted data, unfamiliar cometary physics, or something that prompts us to broaden our definitions of natural and artificial? Please comment and share your theories. This case is anything but resolved.